Assembly language tutorial part 4 submodule 2. In the first video of part 4 we talked about few ways when we could load something into the register, we could add them, and we could access the arrays. We saw some demo as well. We used exchange instruction as well. In this we'll talk about increment, decrement, add, sub and neg. So basically increment, it actually adds something, like it adds 1 to the value. Now it could be register as well, it could be memory as well. Now decrement does the opposite. So the addition instruction, it could be like this. So here we have destination, here we have source. So whatever value we want to add to the destination, we specify that in the source. Now neg, it actually flips the bits. So if we have a neg of EAX, so it would convert the value which is inside EAX, it would make a 2's complement, and that's basically how you convert some number into neg. If you don't know about 2's complement, it's very simple. You flip all the bits and add 1. So suppose you have like 0 0 0 1, so flipping all the bits will make it 1 0 0 0 and plus 1, so we'll make it 1 0 0 1. So the 2's complement of this is this guy over here, right? How do I know it? I did this heck of a lot of times, so I remember this. You will get to remember as you progress through. Directives, we have some more directives. In some of the videos we discussed about, maybe in the first video or second I guess, we discussed about EQU directive and text EQU. Also we used the dollar directive to get the length of the previous string or previous array. So here we have more, like we have offset. So what offset does is, suppose we have a variable like num1, so we want to know which address it is located. It's very useful when accessing arrays and stuff like that. So we could use the offset directive, and so if you look over here, move ESI offset num1, so the address at which this num1 guy is located would be loaded into ESI. Using this approach we could create a pointer as well. Suppose we have an array which is a byte array. Now you create another variable of type byte and you pointed it to my array. So with this we are creating a pointer actually, and now when we do move ESI my PTR, so it is basically accessing this guy over here, the first element. So that's easy it is to create a pointer. Now for C program you would find that you would ask that where is a star there? There is no star. This is how you create pointer in assembly. There is an another directive called length of. It's suppose we have 3 elements in the contiguous memory location or array, so you would get 3. So to get the count of the elements inside an array, you use this directive length of, move EAX length of, and it would give you the length. Similarly we can get the size. Now size would be in terms of bytes, so now num1 is 1 byte, so having this instruction move EX type num1, you would get 1 actually. It doesn't mean that it's just 1 bit or something. What it means is it's just 1 byte. Size of, so size of, it calculates, it's a product of length of and type. So type gives you the size and the length of gives you the item, so you multiply that, what you get is size of. Quite simple, isn't it? Now you could create an alias. Suppose you have a memory location like this, num1, which is a word type and its value is 1234 hex. So you could create an alias for that. How you do that? You do it like this: my label, then use the label directive bit of anything, like minimum is byte. So now you clear out the EAX and move AL. Now this is the lower byte of CX register, like ECX EAX register is 32-bit, so AX will be 16-bit. So AX would be divided into AH and AL. So what it means is, so you have EAX register, so it can be split into 16 plus AX. Now AX is further split into AH plus AL. This is the splitting. Each register is split into like this. In 64-bit we have RAX, which is split into 32 plus EAX. We do not have any names for these, but that's how we do the splitting. I probably didn't cover this, so I thought we could talk about that briefly. So my label, now it's an alias for what? It's an alias for word, right? So my label, the byte is actually, if you see over this, these are actually 2 bytes. A word is a 16-bit container, so my label would be pointing to here. Why? Because it's Little Indian, so the least significant byte is 34. It would be stored first, so my label would actually point here instead of here, because it's a word and it's a byte. So that's exactly what we see here. Like EAX get the value of that, and it's the low byte of AX, which I just explained. The same way, if you want to store at the high byte, you do it like this. Enough of it, let's see a demo. This is slide 2, so this is the demo. I hope I have a demo for that. This assembly is composed of theory plus some demo, and I would probably jump into more of programming, but without theory it wouldn't make any sense if I jump into programming. So we have a label over here, byte, which is for num1. So let's set a breakpoint over here. Okay, so we have AL register, EAX is completely clear, so my label should put 22 there. So let's step through it. Sure enough, we have 22. So the next is AH, which would be 00. This would be the high bytes of AX register, so it would get 11. So you have it, right? It's just moving byte by byte. So that's the sample. PTR. Now there are instances we have seen in previous video, move ZX and move SX. We could copy something smaller into a destination which is bigger. Now suppose explicitly we want to override that. So suppose we want some smaller again to be copied into larger, maybe, but we want to explicitly say that. So this is how we do it. We use PTR. So as you can see over here, num1 is byte 10. So if you do this, this would give an error, right? Because it's a byte and EAX is D word, which is 32-bit or 4 bytes. So these are incongruent sizes. So the assembler would throw an error. But if we have this, it would be perfectly fine. I do not have a demo for that. You could try it out. So this is what happens. So num1 is of size byte. So now we are putting that value into EX, which is of D word. So we use D word PTR. It's like casting. In C++ we have seen casting. It's something like that. Alignment. When CPU wants to access some data from the memory, it sends the address of that in the address bus, and whether it wants to read or write that command is sent over the control bus. So now for CPU it's much faster to read a address which can be divisible by, which is actually even. So if you see that there are two addresses over here, like 4005 and 4008, so this would be much easier for the CPU to access, because the way in computer memory everything is stored is bits, right? It's mostly 8 bits, and then the next sequence again 8 bits, again 8 bits. So now in the odd, what happens is you have to take some sections of the bits from the previous row and some from the next row, which is kind of cumbersome. So that's why, to reduce that issue, suppose we have declaration like num1 by 10, which is offset 4. Now if we immediately declare something like num by 11, so it would be 4, after that we have 5. So this is just 1 byte only, but because this is odd, so it would be, the access to this offset by the CPU would be very slow. What we do is we write align 4. So we have specified that because this is byte, so if we specify that, so the 4 becomes 8, right? We specify the bytes over here. So after that, if we store something, so it would get the next address, which is 8. So that's how it works. Like, we try to push things to have even values so that the CPU can access it faster. Now again, arrays revisited. Arrays are contiguous memory locations. So how do we access that? Suppose we have an array over here which is of d word and stores 3 numbers 10, 20 and 30. Now there are two ways. We use ESI, extended source identifier. So what you do is you use the offset, which we discussed in some of the previous slides. Store the address of that in the ESI, and then this guy over here, so as shown over here, this dereference, you dereference it with square brackets. So you do that, whatever value is actually stored in that address would be loaded into EAX. So the next 4 bytes and next 4 bytes and stuff like that. Because d word is of 4 bytes, so this is increasing in terms of 4. There is another way as well. So you directly do this. Do not have to use offset. So this is the next way. Let's see a quick demo. I have that. So here we are clearing out ESI and EAX. So let's run that. Now EAX is zeroed out. Now we have A. So my array actually contains A, B and C. These are hex values. Now EX has A, so next is B and then C, right? So that's how we access the array. Type def. We could create our own data types. Like if you see over here, I'm creating my own data type, my way type def ptr d word type. It's my way is of d word type. Then I'm creating one variable highway, which is of my way type, right? Either it's my way or it's highway. So when we do this move EAX highway, it would get the data, same data. So yeah, I have a demo over here. So if you see over here, move EAX highway. Now highway is not of any of that type, it's of my way type, and my way is type def ptr d word. So highway is d word type and EAX is already d word, so we could copy highway into EAX, and this is 1 byte only. So let's debug that. EX has some value. Now it will have FF. That's why I always clear the EX using XOR because it could have any value. Probably it's being used by something. So now this is a very rudimentary example. So I give this little exercise to the reader. Those of you who are watching this video, find more meaningful way than this. This is just a use case, and I have actually given hint there. Look for the Hungarian notation. When you are reverse engineering these stuff, so all these things, what you will see is assembly everywhere. So it helps. The more you know, the better you would be at that job. I guess I covered the demo along with, so no separate demo for that. And I will catch you guys in the next video.